I'm Dr. James Millen. I'm Reader in Advanced Photonics at King's College London, and I run the levitated nanophysics group, where we study how physics changes at the nanoscale and how we can exploit those changes. I'm also the director of King's Quantum, our institutional research centre, which is a multidisciplinary research centre with the aim of exploiting quantum technologies in the real world. And I'm also lecturer in quantum theory to the public at the Royal Institution of Great Britain. We're going to take a cutting-edge, very new emerging imaging technology called neuromorphic imaging and apply it to an equally cutting-edge sensing technology using levitated sensors to build a whole new sensing platform, which will be able to do high-speed detection of forces such as accelerations for navigation, rotations, and the detection of very, very small forces which can be used for fundamental physics. We will levitate charged microspheres using electrical fields, and then we will observe and track their motion using very, very cutting-edge neuromorphic sensors. We'll try and understand how to improve that imaging, how to write bespoke tracking algorithms. So we'll be taking data from this system and analyzing it using really cutting-edge data analysis techniques. But more importantly, because these will be used as real-world sensors, we need them to be able to read out in real time. And this will involve the development of hardware and microcontrollers so that we can get signals out of our sensor streaming in a real-time way. By levitating our sensor, we now completely decouple it from the environment around it. We isolate it from its noise in a really protective cocoon provided by the levitation. So now we get all of the advantages of having very, very tiny sensors, which are sensitive to the disturbances we want to detect, but without any of the disturbance caused by noise, which is just information that you do not want. The really exciting thing about levitated sensors is that they have the potential to operate in the quantum regime. So this means that we could operate this sensor as a quantum sensor, which has a lot of implications, but really just means the sensor gets even more sensitive and you can start detecting such phenomenally tiny forces that honestly, I think the scientific community hasn't even come up with all of the ideas as to what we'd do if we had this technology. You can detect individual quanta of light, which are called photons, if you have a sensitive enough detector. You can move these sensors into biological settings and monitor incredibly tiny little bioprocesses, for example, photosynthesis, if you have quantum enhanced sensors for light. This research project really sits at that boundary between fundamental research and applied science.